now.
Do I have to press something? Yes, here, got it. Okay. Well, then again, thank you very much for the invitation. It's very nice to be here, and looking forward to many interesting discussions. So to maybe set the stage a little bit, I want to talk about a paper which we've just got accepted, although it has been in the refereeing process since like 1.5 years, because we had a kind of tough discussion with the referee. I will not say who it was, but I know because he revealed himself on the first round. Yeah, so the paper and the basically the analysis is about the role of gravity in molecular clouds. So I show you how we form molecular clouds and how we do this analysis. All right, then we try to move on. So just a broad introduction, just a few slides. So, I mean, probably you all know that star formation is very inefficient. So if we just do this very simple calculation where we basically measure how much molecular gas mass there is available in the Milky Way, it's about 10 to the 9 solar masses. And the star formation rate in the Milky Way is around 1 solar mass per year. I mean, it might be 3 or so, but of the order. So then you can estimate the typical density of molecular gas between 10 and 100 particles per cc or so for an average molecular cloud, and derive a free-fall time from that density. And that gives you an expected star formation rate of 100 to 300 solar mass per year. But in fact, star formation is much more inefficient than what we expect, because we have only 1 solar mass, whereas we expect 100 times more or so. And so, well, basically you can also see this here in the Kennicotte-Schmidt relation, which relates the star formation rate surface density on the y-axis to the gas surface density. And this is for many different galaxies. We can also do a resolved study now within nearby galaxies, going down to scales of 10, 50 parsec or so, in FANGs, for example. But I mean, I think the remarkable thing about this relation is that it holds over so many orders of magnitudes. And yes, there's some offset for starburst galaxies, which are further up. But in principle, you know, all normal star-forming galaxies seem to be forming stars very inefficiently with an average depletion time of about a gigayear. And so the question now is, why is this happening? So are clouds long-lived? So if you think about molecular clouds being there, the molecular gas is there, we see it. So it doesn't mean it hangs around for a long time and just does nothing. But then if observations tell us that clouds are mostly virialized, how would this happen? Because turbulence decays, so it means that you know, if there would be some turbulent support, that should go away relatively quickly, and then the clouds should collapse. And there's okay, then there could be magnetic fields. This has been discussed a lot by like Moscovius, for example, in the 80s and so on. But yeah, so it's difficult to say how important magnetic fields are. We'll come to this a little bit. And then, well, it could also be that clouds are not in a you know, state of equilibrium, but that they form quickly, and they're also forming stars quickly and are dispersed quickly, as maybe stellar feedback is locally pushing back against self-gravity. So now, just to summarize this, so the question is, why is star formation so inefficient? If you go with the free-fall time assumption, then basically you put in the assumption that your cloud is gravitationally bound, because the free-fall time is derived for pressureless collapse. So it means that it assumes that everything which is there will eventually collapse, and that there's nothing opposing it. So the free-fall time is really the very shortest time you can get out. In reality, we have magnetic fields, we have some thermal pressure, we have shear in the galaxy, turbulence, feedback, and so on. So the question is, do we really have to oppose gravity? Or maybe, so basically, how much of the cloud is bound to begin with? So let's reassess this. Yeah? Is it really true that all the clouds are virialized or not? And so just to elaborate a little bit more on how effective stellar feedback is. So we have seen in many different studies that for that it depends on the cloud conditions, so on the mass and the surface density of the cloud, whether stellar feedback is very effective in dispersing clouds or not. So for for low mass clouds, which we can find also in the solar neighborhood, which have masses between 10,000 and maybe 100,000 solar masses or so, we know that stellar feedback, in particular from ionizing radiation, can disperse the molecular cloud and do this very effectively. However, clouds in the solar neighborhood, they don't have very high surface densities. So the surface density is an important factor here because it basically determines how optically thick your cloud is. And it also is it's something you can measure observationally, but if you assume a typical size of the cloud, say 10 to 100 parsec, you can also translate it to a typical density, meaning that if clouds have higher surface density, they are also expected to have on average higher number density, so in volume, right? And for the ionizing radiation, the recombination rate goes with the number density squared, meaning that if you have higher density gas, you would actually recombine a lot more efficiently. Your H2 regions are a lot smaller, and so it's very difficult for the ionizing radiation to disperse the clouds. And that's why people have been thinking about radiation pressure becoming more important than taking over the role of ionizing radiation when you go to higher surface density clouds. But still, if you do simulations of feedback with radiation and radiation pressure, the star formation efficiencies which are achieved are very high for high surface density clouds. So you can see here one study by Kim et al. From 2018 where they go up to 60% or so with radiation pressure feedback for clouds which have 1,000 solar masses per square parsec. Then here is a study by Grudich from 2018, basically going almost up to 100%. This is here for clouds with 10 to the 4 solar masses per square parsec. At 10 to the 3, they are also around 60% or so. And here is one from Howard from 2017 showing the same trend. So basically, well, this is a time evolution, but for different clouds with different masses. And when you go to these very high mass clouds, it becomes very difficult to have feedback stop the star formation. So star formation in dense clouds is very efficient. And so even if you get away with it, so to say, for low mass clouds, for the high mass dense clouds where most of the star formation actually is happening, it doesn't help you any longer. And this is also seen in a semi-analytical model by Rana et al. This is this warp field 1D model where basically you can get to very, very high star formation efficiencies for higher surface densities. The star formation efficiency here is the color, and it also shows you go up to more than 50%. In particular, when you have, it depends a bit on the density profile and so on, they play with this. They also mentioned that cloud geometry matters. And in particular, if you have not spherical clouds, but sheet-like clouds or filamentary clouds, you also get a different boundedness of the cloud, of course, because you can have low-density channels in between high-density regions. Whether it makes it easier or more difficult to disperse the cloud is actually questionable, because if you look at the work by Jim Dale, where he had basically virialized cloud collapsing, forming dense filaments and forming massive stars. And then these massive stars were blowing out radiation feedback. He saw that there was very little effect of the radiation because the dense filaments had collected most of the mass in the cloud, and it was very difficult for the ionizing radiation to do anything to that dense mass. So once you have the dense gas mass, the feedback is it's very hard for the feedback to push back. So the question is, are we with how much of the cloud is in this state that it's so dense and bound that you actually have to push back? So this is what I want to get at today, right? And so for that, I would like to introduce the SILCC simulations, which we're doing for a while now. So basically here, we are taking a piece of the galactic disk. It's for solar neighborhood conditions, but we have also done other models now varying the surface density and recently the metallicity. But today I want to focus on solar neighborhood. for the molecular clouds which we are forming. And we have all kinds of physics here. It's run with the flash code. If you're interested, you can ask me later. But I want to show you a movie first. So what you can see here is a typical simulation, one of our latest ones, which also has cosmic rays. Sorry, this is jumping a little bit, my mouse. So here, basically, we have density slice, temperature slice, and the cosmic ray energy density. We inject cosmic rays with supernovae. 10% of our supernova energy goes into cosmic rays. We have a chemistry network, so it's a small network, but we can follow the formation of molecular hydrogen. We also have atomic hydrogen and ionized hydrogen. You can see here bubbles which are formed by the ionizing radiation from massive stars, which are sitting in these little clusters, which are shown as points. And basically, we follow each individual massive star within the clusters, where we randomly sample the mass of each star once it is forming from the IMF, assuming a Salpeter slope for the high mass end. So, and you can see that, so then we follow actually the track. So the supernova explodes at the end of the lifetime. The lifetime depends on the mass of the star and so on. And there are also stellar winds in the simulation. And yeah, all right. So, but actually, so then we did a few different studies. For example, what we looked at was the effect of different feedback mechanisms for star formation. And so here we basically played God and switched on and off different feedback mechanisms. So in particular, we ran one model where we only have supernova feedback. This is this blue point S. Then we have supernova and radiation feedback, so ionizing radiation in this case. Supernova and wind, so no radiation, but only the stellar wind. Then we have supernova wind and radiation, supernova wind and cosmic rays, and supernova wind, radiation, and cosmic rays, everything. And you can see that basically the supernova feedback alone produces star formation rates which are way too high compared to the observed data, which is shown in the background. And then as we switch on feedback, basically we go down in star formation efficiency. And in particular, the radiation is very effective on these scales because, yeah, we are not resolving the very dense gas on the scale of the SILCC simulations. And so here we can limit the star formation quite effectively. Basically, what happens is that the radiation feedback limits the growth of the star cluster forming environment. So the accretion is shut off, and therefore so early on, basically, because radiation becomes effective immediately when massive stars form, not as the supernovae, which only explode after 3 to 40 mega years, right? And so by basically, yeah, regulating the accretion onto the star cluster forming environment, you can get values which are consistent with the Kennicutt-Schmidt relation on these galactic scales.
So is this averaged over tens of mega years?
This is averaged over, I think, 150 or 200 million years. Mm-hmm. Yes. And so there's a little spread in surface density. We start with 10, but then some mass goes into stars. And in fact, here a lot of mass goes into stars for the supernova. That's why there's this huge spread. Yeah. And then the variation in vertical is because we have periods of more or less star formation. Yeah. But okay. So on the galactic scales, but this model, basically what I want to show you is that this model basically assumes within star clusters 100% star formation efficiency. And now we argued about this a lot in our collaboration, because you might say, why are you doing this? Why don't you just put 10% into stars and the rest? What is the rest doing? So then we did this once, and what happened was that, of course, when we hide 90% not doing anything in our zinc particles, then there's very little feedback, and the star formation rate explodes. I mean, like everything collapses. There's no feedback, basically. So it's similar to a no feedback run. So so then we were like, okay, still, if you look on the scales of several hundred parsec, it seems to be okay that you have a high star formation efficiency on small scales. So I think from these large scale observations, you cannot tell. And I think this is why FANGS is so cool, because we need to go to the smaller scales and see what's happening there. And I mean, we also, of course, can look in local molecular clouds. So, but what we can do in the simulations is that we zoom in. And we do this in the so-called SILCC-Zoom project, where we basically know on the large scales where molecular clouds are about to form. And then we go back in time and we allow the grid to adaptively refine such that we follow the formation of the cloud with high resolution. And so we go down here to 0.1 parsec resolution. We also tested this going a little bit lower, but say around 0.1 parsec. So this is just one movie where we also have feedback. You can see it's 3D. It's rotating around. Sorry, just hanging a bit, I think, because of my internet connection. Yeah.
These are no magnetic fields here. Is that right?
This was an MHD run, yes.
This is MHD.
Yeah. We did MHD and non-MHD runs to compare. And so this is just two clouds which are plotted here on the top row and on the bottom row. And I show you the distribution of atomic hydrogen, molecular hydrogen, and CO. The CO is scaled up such that we can use the same color bar. And so basically what you can see here is that we get this kind of onion-like structure or scrambled egg structure, whatever you like better, where the CO is tracing the densest environments. The molecular hydrogen is tracing also a little bit lower environments. It is because molecular hydrogen forms at slightly lower visual extinction than CO. So for CO, you need slightly higher shielding, so to say, from the destroying interstellar radiation field. And then everything around is atomic hydrogen from which these molecular gas formed in the first place. And so there's quite a complex structure. And we can also see that as a function of time, when we look at the formation of the cloud, so to say, we start at a point where we have most of the gas in atomic hydrogen, and then the molecular hydrogen builds up over time. So this is shown here in solid lines for these two clouds. The molecular hydrogen fraction and the atomic hydrogen fraction goes down. And we have looked at where the molecular gas is forming. We find that there's that basically the turbulence allows the molecular gas to form more quickly than what would be predicted from equilibrium models. Because there's like this FIST formula where you can say that the H2 formation timescale is about 1 gigayear over the number density. And we can measure the number densities in our clouds. And so if we would have an equilibrium model, then basically it would take much longer to form the molecular gas. But because there's there are shocks and density enhancements, turbulence, then you can have a quicker molecular gas formation. This is also something Simon Glover has looked at in 2010. So now we go and do a structure analysis of these clouds. And we do this by using dendrograms. We take astrodendro actually in the end search for substructure in these clouds. And you know that with a dendrogram, you get this, you basically put in density thresholds, and then you get a level of structures, which you can display in a sort of tree, which we have done. And then we have done some different analysis. So we've done a structure analysis looking at whether these clouds are filamentary, spheroidal, or sheet-like. And we have also done a virial analysis, which I want to talk mostly about today. The structural analysis we have done by basically computing the moment of inertia tensor. Then you can get the eigenvectors and eigenvalues. And from that, you can, by doing the ratios of those, you can figure out what kind of structure you have. And we see that actually a lot of clouds are sheet-like. But when you go to smaller scales, then you also have filaments, and only on the smallest scales we form spheroids. So it's kind of a general picture that you have sheet-like clouds on the large scales, which form filaments inside, and then there are cores forming inside the filaments. So then this is just showing you, gallery of the different clouds. And so we will compare a number of clouds now, which basically I will put all the structures of all the clouds in one plot. unless we distinguish between hydro and MHD. So we have here 2 hydro clouds, which we put in the sample, and the rest are MHD clouds. So here we use a typical magnetic field strength of 3 microgauss in the beginning, and then it's like developing. And all the clouds have masses around 100,000 solar masses or so in total gas mass. You can see here the sheet-like structures on the large scales for a few. So now let me go to the virial analysis. So first of all, we said, okay, let's do the same as one you would usually do, and just compare kinetic energy and potential energy. And then you can plot well, this is actually not using alpha at all, but you can plot the higher relation, which is Larsen, but then in addition to that, you have basically here you would, if you would have a Larsen relation, it would be completely flat here. But Haier showed that there is a surface density relation in these clouds, and that basically for higher surface densities, you would also have higher values of velocity dispersion over size, basically. So this is size to the 1/2 power. So we did this for hydro and MHD clouds, and there was, we could kind of recover the observed trends, I would say, from this. We see that there's a clear dependence on the surface density also, which is also seen in observations. And now the question is, how do the different terms contribute to this? So we have now plotted here the virial parameter. So here we have between 1 and 2 color-coded in red, because this is stuff which is usually thought as virialized, right? And we have done this for hydro and MHD clouds. Here's a little bit earlier time, here's a little bit later time. I wanted to show you this time evolution. Just focus on this for now. The other stuff we will look at more in detail later, because there's basically no real statistical difference between different times, only that for earlier times you have fewer substructures than for later times. So as the cloud develops, you form basically more cloud, and so you form more substructure. What we can also see from this plot is that the empty symbols are structures which are dominated by atomic gas. So they are more than 50% of the mass of the structure is in atomic gas, and for the filled symbols, more than 50% is in molecular gas. And so the atomic structures are always like totally super virial. So there's there's basically, there are a few on the large scales here which are which have low virial parameters, but most of them are really super virial. And just to keep in mind, most of the dense structures form from the atomic structures in the first place, right? So somehow this tells us something. Right, and then to first discuss the impact of the magnetic field, we look here at the time evolution of the ratio of the magnetic energy to the potential energy, and basically here we took a mean over all the structures, but we distributed all the structures in 3 different types. So we have all of these atomic structures in red, we have all molecular structures in blue, and then we also look at molecular, but with densities higher than 10 to the minus 20, so dense molecular structures. And you can see that for the atomic structures, the magnetic field, so this is magnetic to potential energy, is very important energetically. So magnetic field really dominates here over the gravity. And it also dominates over the kinetic energy for the atomic structures. So magnetic fields are very important for the fluffy atomic gas. But it's very different for the molecular gas. So here the magnetic field becomes totally unimportant compared to potential as well as kinetic energy. So there's some transition where, between being magnetically dominated or not. Now the question is, does it really mean that there's a transition, that structures which were magnetically dominated lose magnetic support and become not supported? Or does it mean that there's a selection effect where structures which are magnetically dominated never become molecular, they just stayed atomic and are held up by the magnetic field, and just the other ones which are not supported by magnetic field can develop molecular gas and become dense. So this is a different discussion. Maybe for later.
Maybe 5 minutes?
Yes. So then we looked at the other terms. So this is, sorry, just a little bit small. I hope you can see on your screens better. So there's thermal energy to potential energy. And as expected, so the color here is density. If we go to higher densities, basically there's no thermal support. This is expected, right, for dense structures. There is some thermal support for the atomic gas. You can see some of the atomic structures are way up here, so it means they're warm. Then kinetic energy actually can balance gravity quite well. So you see that just kinetic over potential already brings you up to almost virialized. And if we put everything together, so this is kinetic, thermal, and magnetic over potential energy, then we have basically no structures which are below 1. And but there are many structures which are below 1 and 2. Now the question is, does it mean that these structures are gravitationally bound or not? So this is now the question, because actually quite some substantial amount of mass in all of the clouds is contained in these structures. So then this is again showing you a time evolution just to convince you that really the atomic structures are never virialized. And for the molecular structures, you can argue about it, but the dense molecular structures, they become virialized. And this is the same for hydro and MHD. As we expect here, the magnetic field is not so important anymore. So now let's do a full virial analysis, because in the simulations, we actually have access to all the terms. And so we can look not only at the volume terms we've just discussed, but also at the surface terms. And we can not only look at the potential energy of a structure, but also at basically the gravitational torques which are acting on the structure. So the total virial alpha, which I introduce here, now is the ratio of the sum of all the volume and surface terms for kinetic, thermal, and magnetic energy. And for the potential energy, it is the volume, so really the self-gravity and the tidal forces, so to say. Okay, let's not go into detail. There's a relation between the two, which is not necessarily one. You can see there's a scatter here. This is the one we looked at before, the typical volume virial alpha, and this is the total one. In particular, there are some with low total virial alpha, which are not existent. I mean, there's basically nothing here. So it means that surface terms matter. I will skip this. So now let's put this onto some diagram, which relates the sum of potential and volume plus surface terms on the y-axis to the ratio of these terms on the x-axis. This has been introduced in a paper by Sami Dip, actually. And he introduced also these 4 quadrants, where basically you can distinguish between the dynamical state of the structures very easily. So here, if you find a structure up here, it's primarily dispersed by volume and surface terms. If you find a structure up here, it's primarily dispersed by tidal forces. If you go down here, you are in the region where you can have bound structures. But here you have something which is bound, but not by self-gravity, but rather by ram pressure or some confining magnetic term, something like that. Only when you go to this quadrant 3, you can have something which is possibly bound by self-gravity. And here we distinguish between potentially bound, so these are all the structures in quadrant 3, and structures which are definitely bound. So here we can basically measure if the leading energy term is the potential energy term, then we say, okay, this is really gravitationally bound. There's no doubt about it. So now let's put our structures on this diagram, and we color-coded here the leading energy term with the color. So you can see that there are actually lots of structures which are not bound at all. Some are affected by tidal forces, not so many. But then there are many which are actually bound. So all of the ones down here. But the ones here, remember, they are not bound by gravity, but they are bound by other means. So mostly they're actually bound by ram pressure. So this is the kinetic energy surface term, is basically ram pressure. But then there are some gray points which are bound by surface magnetic fields. Then over here, we have some which are really gravitationally bound. We can, if we plot the leading energy term in quadrant 4, this is the plot down here, and in quadrant 3, just to visualize this more, then we can see, okay, some really are definitely bound by gravity. Then there are some which have a very important kinetic energy volume term. Now we had a long discussion with the referee whether this kinetic energy is turbulent energy or something, or whether this kinetic energy actually comes from gravitational collapse and is just, you know, showing up as the leading term. So what we looked at in detail is whether these guys here have as a second most important term the potential energy or not, and so on. So, and I think it's fair enough to say that all of these structures here are potentially gravitationally bound, because we cannot tell whether the kinetic energy comes from gravitational collapse or not. So, all right, it's very difficult.
You could if you looked at the velocities, I guess.
Well, yeah, we can. What we have done is that we looked at accelerations and the angle between the acceleration vectors and so on. So you can see that for some of these structures, you can start to get alignment between the self-gravitational acceleration and the velocity. Yeah, so this is a hint that there is something coming from that. But yeah, it's up to some. So now to come to the main message. So if we look at basically now the results for all of our clouds. So here we have the largest bound scale on the top. And here we have the mass in bound structures. And this is for these potentially bound structures. So basically all of them which are in quadrant 3. And here for the definitely bound structures, which have the leading energy term being the potential energy. So, and what we can see is that the potentially bound mass fraction is typically about 50% or so, and the definitely bound mass fraction is below 10%. So there's only very little mass which is definitely gravitationally bound. And then for the largest scale, you can see that potentially bound, you have a number of clouds. So the largest scale we measure in our dendrogram is here indicated with this red bar. And so there are some clouds which have potentially bound structures on large scales, but definitely bound structures, not really. So there are only small scale stuff is really definitely bound. And so basically what the takeaway message is that I think there's very... there's indication that just about a third of the clouds, at least in our sample, has about 50% or so of the mass in potentially bound structures. And I guess only a fraction of that is definitely bound. So it means that only a small fraction of the overall cloud is really self-gravitating to begin with, right? And I think to determine this, is one of the main questions which I want to raise. And I think this is also what I would like to discuss now, because the question is really, which I have, is how bound are molecular clouds? Because if you do not have bound clouds, then you don't have to oppose gravity to begin with. And so, yeah, as I said, our analysis shows that, yeah, maybe a third of the clouds have something like 50% of the mass in potentially bound structures. So now this has been for clouds which have, around 100,000 solar masses, as I showed you. Is this applicable to denser environments, more massive clouds? That's a main question, because we have a lot of star formation in massive clouds. And how to connect to observations, because the terms we all looked at now are not generally accessible by observations, right? All of these surface terms and so on, even the magnetic fields, are very difficult to assess. And so, but the goal would really be to constrain mass and energy flows, of course, from large to small scales and back. And the computational challenges I see is that we actually could do with more resolution, in particular when we go to more massive clouds. We have a lot of physics, so we need robust schemes. We're fighting with the MHD sometimes, and for more massive clouds becomes even more difficult. Even the chemistry there is acting up sometimes. And then, of course, you need statistics, because you've seen that we have quite a scatter here, right? And so if we only look at one object, we cannot tell we really need to do a lot of objects, I think, overall. So, and this is it. Thank you.
Great, thank you very much. So let me stop the